Next, we have a presentation about contactless and nanoscale enabled future healthcare. This talk will provide overview of ongoing research on contactless sensing for remote monitoring in University of Glasgow. In addition, a brief overview of ongoing activities on future healthcare paradigm at nanoscale will be presented as well. We have Dr. Qammer Abbasi to present. He is currently senior lecturer with the James Watt School of Engineering, University of Glasgow, UK, the deputy head for communication, sensing and imaging group, program director for dual PhD program. He has contributed to more than 350 international technical journal and peer-reviewed conference papers and 10 books, and has received several recognitions for his research, including URSI Young Scientist Awards, University Research Excellent Award from TAMUK in 2 consecutive years, and multiple others. So please join me in welcoming Dr. Qammer Abbasi.
Thank you so much, Sanawullah, for the introduction. And I would like to thank all the team for the project, for inviting me, especially Professor Naeem Ramzan, for inviting me to present this research. So I will be talking more about the futuristic concepts, which might not be applicable in short term, but those are the future enabling mechanism which can basically enable future healthcare. So my talk will be in 2 parts. First will be how we can get rid of these wearable and implantable devices and coming up with contactless sensing. And second one is, I would say, it Vision 2050, which is about nanoscale healthcare. So before moving forward, so I would like to give you a brief overview about University of Glasgow. It's 4th oldest university, established in 1451 and home to 9 Nobel laureates. And I belong to Communication Sensing and Imaging Group, where I'm deputy head, and it's a multidisciplinary group with more than 100 members with a diverse grant portfolio and the team members working in all domain of protocol stack. So the team is involved in some of the major grants related to healthcare, including recent one, EPSRC Quest for Healthcare, Qammer for Healthcare, government funded non-invasive 5G New Thinking Project for Healthcare, and Scotland 5G Center, which is a national funded center where I am actually leading the use case for healthcare and IoT based use cases. So the projects involve a lot of industrial and academic partners, both from within UK and outside UK. And let's move to the talk. So before moving forward, the main thing is, what is the motivation for all this research? So according to US Bureau of Census, the number of elderly people are predicted to be 70 million in USA and roughly 15 million in UK by 2050. And this increase in rate is very fast. And it's predicted that ratio of elderly people rate in UK by 2030 will be around 24%. And what it's causing, that is healthcare expenditures. So if we have more elderly people, there are chances for more health expenditure. And the prediction is that by 2050, by 2060, UK will be spending 12% of its GDP on care. And this is scary. So and the major cost of this comes from hospital admissions and the staff who take care of the patients who are admitted in hospital. And sometimes uh, the visit to hospital is unnecessary because something can be cured or diagnosed away from hospital as well, which will save the cost for transport, which will save the cost for medics, which will save the cost for hospital. So what is the solution to that, to reduce this cost? The ultimate solution is remote health monitoring, that how you can monitor yourself at home, or instead of moving from doctor-centric concept to patient-centric healthcare concept, where one can control or monitor his or her health So there are so many commercial products available in market around wearables, including Nike Bluetooth shoes, and all of us have these smartwatches with us. And there are also many implantable commercial products available as well. One of my favorite is this wireless endoscopy, where a capsule with a camera goes inside your body, takes pictures or images and send it outside. But here are some issues with these wearable and implantable devices as well, that these wearable devices are intrusive. Subject needs to wear them all the time. Implantable devices are invasive, where you need to do surgery. And if you want to use camera-based devices, which are vision-based devices, they are not privacy preserved. Their cost is high. So ultimately, whatever technology is available nowadays in terms of remote patient monitoring or remote subject monitoring has some drawbacks. So considering those drawbacks, we thought, can we solve this issue by using ambient RF signals around us, which includes Wi-Fi signals, which include mobile signals. So can we use those signals to monitor someone's health? And there are certain indicators for someone's health, which includes uh, activity, which includes vitals, and we can look at those parameters to basically look at the health of someone. So the main idea here is that the Wi-Fi signal, or I would say RF signals, they are omnipresent. And when these signals go from one point to another point where we have a transmitter and a receiver at the other side, there are certain fluctuation which occurs in the signal, which are called basically channel state information. There are certain changes occurs in channel state information amplitude. For example, Wi-Fi has 64 subcarriers, where basically we are using OFDM, which has 64 subcarriers. So those subcarriers have channel state informations, and those channel state information, when they basically reflect are different from a person, they have certain changes incorporated in those signals. And by applying advanced signal processing and machine learning, we can extract the information out of those signals. And I will talk about some of the research work we did. But this is the solution to overcome wearables and costly camera-based technologies. And then how we can overcome implantable issues. So as we are moving towards nanotechnology, and the idea is that in future we are going to have a single nano sensor. Basically, we are going to swallow a capsule which has hundred thousands of nanosensors in it. They can go inside our body, they can disperse inside our body, and those nanosensors can measure either cell temperature or biological changes, and then they can relay that information to the doctor to make some kind of decisions. And this is the envisioned nanoscale healthcare architecture I proposed back in 2016, that these nano machines or nano sensors will be small in size, so they cannot make decisions themselves. So they need to work in a network. So there will be some nano machines who will be measuring cell temperature or biological changes, transmitting it to nano router, and then that nano router is much larger in size in terms of capacity. It can aggregate and can forward the data to our traditional network in 2050. We don't know, it might be 6G, 7G, or 8G, whatever it will be. And then we can process that data and can send that information back. Now, one question is that how these nano sensors going to talk to each other. And my background is in bioelectromagnetics. So back in 2015, basically, we did some preliminary pioneering research that we can use terahertz as a mode of communication for connectivity between those nanosensors. And terahertz is a very high frequency, well above current mobile communication frequencies, and it has certain advantages which I'm skipping because of the time limitation. So this is the envisioned future proactive predictive in-home monitoring system which will come into place in next few years, that we will be having sensors uh, which includes environmental sensors, which include non-contact sensing system. Then there will be some nano sensors on the person, either a patient or a subject. And these sensors fused information can be transferred to the back end where advanced machine and deep learning algorithms can process that data, and then the healthcare can take decision based on the output of that data, and then it can provide intervention to the subject. So this is how a future healthcare system will look like. So now I will be touching about some of the works in two domains I mentioned. One is contactless sensing and the second one is nanoscale healthcare. So our vision is that can we make the healthcare totally proactive, means before something happen, we can inform the patient that, for example, if someone has basically certain changes in their gait analysis, this can lead to certain kind of disease. So by looking at that disease and doing some prediction, we can make a proactive decision that, okay, this person can have Y disease, so he or she needs to go to the doctor. So the parameters that can be input to the signal processing engine, which is a deep learning or machine learning, can be either uh, the gait analysis or the vitals of the subject, where we can perform machine learning or deep learning to make some decisions. So what we did in past is that basically for a single subject in a lab controlled environment, we used this wireless sensing to predict or to classify different activities for the subject with an accuracy of 90%, which shows that we can use this uh, contactless sensing for looking at the gait of some subject. Then an interesting work which we did, again, this was a pioneering work we did, that we use these contactless or RF signals. In this case, it was an ISM band at 5.2 gigahertz to monitor a breathing pattern for a subject. And we compared our results with the ground truth data by using commercial off-the-shelf breathing belt. And we found out that we can basically detect breathing abnormalities with an accuracy of 91%. And this has a great advantage in current COVID scenario, where breathing is one of the parameter for a patient. And if doctors go close or nurse go close to the subject, they can have uh, an issue of getting COVID. So this technology has a great advantage where at a distance of up to 2 meters, breathing patterns can be observed for the subject. Then other thing we did is basically for a Parkinson disease. So what happens in case of Parkinson disease is that a gait of a person is basically frozen. So we mimic that scenario in the lab, and by using these uh, RF signals, we basically predicted the freezing of gait scenario. And then Professor Ramzan was mentioning about Kinect, that how he and his teams are using Kinect to do various kind of basically diagnosis or whatever, I would say, monitoring. So what we did, that we used basically these wireless signals to estimate human pose, which can be very useful in case of injuries for rehabilitation. So we basically, if you can see on the top one, our ground truth was alpha post. And in this case, our ground truth was Kinect version 2. And these dots are the estimation of pose using these wireless signal. And accuracy was considerably very high. So up to now, basically, what I have shown is that we can use wireless sensing to predict or to monitor a single subject vitals and gait analysis. But when we move to the challenge of multi-subject, for example, in a care home where we have multiple subjects, So it's very difficult to estimate that if this heart rate is for person A, B, or C, or whatever uh, activity signals we are getting, is it for subject A, B, or C? So this is a very challenging problem because we have a single wireless signal. So we have to extract information from that. So for that, basically, we are currently working on. So it is work in progress. That's why I wrote. So we have basically accurately detected 3 subjects in a closed room in 2 different postures. Similarly, for a multi-subject breathing, we are successful in estimating the breathing pattern for 2 and 3 subjects with a very high accuracy. And in this case, basically, this is the average power spectral density, which is basically coming from these wireless signal, and these dark lines are from off-the-shelf sensors, which was a polar sensor for breathing and another sensor for heart rate. And this is basically heart rate for 3 subjects at 2 different instances. And you can see again that these vertical lines are the ground truth data from a polar sensor, and these peaks are estimation using wireless signals. And you can see that there's a considerably high accuracy. And as I mentioned, this is work in progress, and it has so many applications. We were approached by the jail that if they can monitor their people remotely in jails for their breathing and vitals, COVID, whatever you name it, it has application everywhere. So we are going actually one step further. So if we are in a room, how we can localize a person, that is another challenge. So we are basically, my background is in electromagnetic. So we are developing a special kind of concept, which is called wireless on the wall. So if you have knowledge about wireless, what we do in current scenario is that we either manipulate transmitter or receiver to improve quality of service. But what we are proposing is that we can manipulate the channel. We can basically manipulate the wave which is going from transmitter to receiver. Either we can focus it, either we can basically track a subject. So we are basically designing these surfaces. These are called intelligent reflective surfaces, which are basically meta surfaces. You can see on the left hand side, we have developed a hardware, and the idea is that how we can improve our contactless sensing accuracy, because in the previous case, you have seen that we can basically estimate vitals and gait analysis for a single subject, and there are around 80 to 90% accurate. But if we want to basically track a subject, or if we want to increase the accuracy for multiple subjects, we need to basically control our beam which is inside the room, and that is basically called intelligent reflective surfaces. And it has applications beyond vitals and activity, which is basically we can measure gestures. So we are basically using this concept in one of our project where we are trying to make an intelligent hearing aid device which can basically monitor the lip reading and then can process it to remove the cocktail noise from those hearing aid device to make a futuristic hearing aid device. And this is the concept of intelligent reflective surfaces. If you don't know, this figure clearly explains the concept of intelligent reflective surfaces. I think I have very less time left. So the main takeaways from this work is that contactless sensing has a potential to support independent assisted living, but still it is far behind, and there are so many challenges which needs to be solved. Then the next thing is nanoscale healthcare, which I was mentioning, that this is another concept we proposed in 2016, that how a future nanoscale healthcare will look like. So basically what we did is that basically, because there are no nanoscale nanosensors in the market yet, so we'll try to basically see that if we can use terahertz as a mode of communication for nanosensors, and can we use that to detect different kind of anomalies. So most of the work is done in lab. So we looked at different tissues. So I'll be talking about skin here only. Skin has different layers, dermis, epidermis, and subcutaneous layers. And what we did, that we are working closely with medical doctors. So we took the real skin sample and try to work on that in the lab. But the issue is that our human body is composed of so much water content. So before we take that sample to the lab, water evaporates and the results have an issue. So what we did, that we basically cultured skin in the lab by using fibroblast cells from the rat, and we cultured that skin by using fibroblast cells. So there was a long procedure which is given below, and then we use that collagen sample to measure the parameters of that sample so that we can come up with the link budget for the future nanosensor. So this is terahertz time domain spectroscopy system, which we uh, were working on in Queen Mary University of London. And this is part of the project from Qatar National Research Fund, which I was leading for from 2013 to 2014 to 18. And the work involves measurement and simulation as well, because this measurement setup is very expensive. So we try to mimic everything in simulation as well. And then what we did was which had a great significance, that as we were working closely with medical doctors, so we basically try to see that if we can basically detect the cancerous tissues, can we detect melanoma, can we differentiate between melanoma and normal skin. So what we did, that we can, as we were preparing these artificial skins ourselves, so we controlled the density of fibroblast cell which combines to make a collagen, and we used a melanoma and normal skin, and we found out that we can basically differentiate by using terahertz sensing, which is a future paradigm for nanosensors, to differentiate between normal skin and melanoma. So this is breakthrough research results which we presented in 2017 for the first time in literature, uh, a channel model for in vivo nanoscale communication at terahertz, and you can see that there is a high degree of correlation between the proposed model and the measured results, with an error of only 2.10 dB, which will basically change the future of healthcare, which is enabled by nanosensors. So the main takeaway from this research, because I didn't present all results, that we can achieve maximum transmission distance by using in vivo nano network sensor. The maximum distance we can achieve is around 1 to 2 millimeter. That's why we did some research for relay based communication as well, that how we can extract information from inside gut to outside the body, because the distance from stomach to outside body is around 6 to 7 millimeter. But we found out that the maximum transmission distance we can achieve is 1 to 2 millimeter, because body is very lossy, and as we go higher in frequencies, losses increase. So we proposed a concept of relay based communication, that sensor one pass information to sensor two, two to three, three to four, and then we can get information outside the body. Then because we are working at very high frequency, so we can achieve a very high channel capacity of up to 100 terabits. But having said that, as I say, that this is very futuristic research. So there are so many challenges left and much work needs to be done. So with this, I'll stop here, because I think I'm exactly on my time, which was up to 7:20. So there are some of the books which I wrote with my colleagues in this area, starting from antennas, variables and implants, contactless sensing, and some of the activities we are involved in, because we are not only focused on research. And with me, this is First Minister of Scotland, who basically inaugurated in 2019 Scotland 5G Center. So with this slide, I'll stop here, and I'm very open to questions if you have any questions.